at exact equation. Exact equation. Exact equation is a first order differential equation. Let us take a look at a typical question in exact equation. 3x into y minus 2 differential x plus the y component, and the y component part is s cubed plus 2y differential y is equal to 0. Now, when you are to solve exact first order differential equation, the first thing with this relationship, if for example you have this expression and we can increase this degree by putting x here. So let's make here xy rather than y. So we expand to give us 3x squared y minus 6x differential x plus s cubed plus 2y differential y is equal to 0. So this can be likened to the p is a function of s comma y differential x plus q is a function of s comma y differential y is equal to 0. So in first order exact differential equation, we say partial p function of two variables x and y respect y is equal to partial q function of x comma y respect x. Once they are equal, the equation is said to be exact. This is the condition for exactness, for exact first order differential equation. Now let us partialize. Partial derivative of x of 3x squared y minus 6x with respect to partial derivative of y. This will give us, we're partializing this function. Assuming this function is p function of x comma y, we will now be having partial differentiation. We only target y and differentiate y. So we have 3x squared times 1 because y is 1, which is 3x squared. Now we'll further the expression by going to the partial derivative of the other side, which is the cube, which is s cubed plus 2y with respect to partial x. When this is differentiated, we get 3x squared. You can see that this is an exact first order differential equation because they are equal. They are equal. So the next step is the solution methodology. In the solution methodology, we have to write function of x comma y is equal to the integral of the first function, which is, when expanded, which is 3x squared y minus 6x differential x plus arbitrary constant k in function of y. Because we are integrating with respect to ds, the constant should be with respect to y. So now, this is the first methodology to get the solution to exact first order differential equation. So in this process, we will integrate the first part and later compare it after partialization with respect to y with this other side. So we integrate, and the integration gives us s cubed y, because this will be 2 plus 1 over 2 plus 1. The 3 down here, cancel this 3 to give us s cubed y. Now minus, with respect to x, this will give us 6x squared over 2, which is x squared, plus arbitrary constant k, function of y. Now, take note that the integral relationship has the capacity to make even the expressions, so that obviously when we relate with the happenings here, you see that the relationship of the concept itself must be in tandem, with the expected deviations, so that when the relationship is connected to the relationship of integration, you see that this is 3x cubed over 3, cancel this, you have s cubed y. So the s cubed y you have here is quite a different phenomenon in the relationship. So what we do is to relate it further by integrating the other component. Now the other component that we have here that has been reviewed that gave this, when we integrate this and compare with this, we get the same answer when compared. So progressively, we now have partial derivative of f, function of s comma y, with respect to partial derivative of y is equal to, we are partially with respect to y, we have s cubed will reflect, s cubed will reflect, minus, because we are partializing, minus 0, because there is no y here, down plus decay dy, equation 1. So progressively, after getting that equation 1, we are now going to make comparison of equation 1, which is s cubed plus decay dy is equal to the other part of the question, which is s cubed plus 2y. Leave the y out of it. Now, the essence is to get k. In course of comparison, you will see that exactly a value exactly will reflect, which is s cubed here. So they go off. Now we have decay dy is equal to 2y. So transfer the y. Decay is equal to 2y differential y. Now we integrate to get k. Integral decay is equal to 2 integral y differential y. K is equal to 2y squared over 2 plus arbitrary constant c. When cancelled, k therefore is equal to y squared plus arbitrary c. Now this is your equation 2. When equation 2 is added to the first expression we got, let's call this equation 1, and this is equation 1 star. 1 star. This is equation 1. So inserting this in equation 1, we'll be having, therefore, function of two variables x comma y is equal to s cubed. Is equal to s cubed. That is the initial equation y minus x squared plus the whole of this y squared plus c. Because this was the value we got here. It has to be substituted in this position because equation 1 gave us this without being partialized. The function of s comma y, when integrated, gave us this. So we have to source for k function of y by this methodology by partializing the already integrated function with respect to y. We partialize it with respect to y. So when partialized, so that you can have, we integrated this as a function with respect to s. So we now compare and get the answer.